Okay. Right, so let's see. So we're continuing our discussion on microvalves and micropumps today. Last time we talked about different valve types. Let me make sure the recording. Yeah. Last time we started recording, talking about different valve types. So we'll finish talking about those, and we'll start getting into the micropumps today. So as a quick review, we looked at a few different types of valves last time in class, different valve technologies, and ways that conventional valves work at the macro scale, okay, at the macro size scales. There's many different types of valves that are used in industrial applications, in home applications, in scientific applications, and the things that are used most commonly in microfluidic devices are the pneumatic valves. Okay. There are other valves as well, but we started talking about these first because these are the most common. The way that the Quake valves work is by displacing. You have a membrane in between two fluid layers. The top layer is the pneumatic layer, so there's a gas pressure, and that gas pressure is provided by solenoid valves that we talked about here. There's external solenoid valves that you can get that are part of your laboratory setup. And those solenoid valves can either supply high pressure or low pressure into your chip. Okay, so this this line that you see here, this is the pneumatic control line. So there's two channels. One is where there's gas flow, and one where there's fluid flow. In the gas flow channel, if you increase the pressure, so if you turn on that solenoid so that you have a higher pressure in the gas line, the membrane deflects down, and that blocks the actual fluid channel below that. All right, so we talked about how that technology can be scaled up into a large-scale integration where you have thousands of valves on a chip, and you use this clever a binary multiplexing scheme so that you need so that you require fewer external control lines. And if you use this binary multiplexing scheme that Stephen Quake developed, you can control n fluidic channels with 2 times log base 2 to the n control lines. It's a logarithmic function. So the higher the number of channels you go, the number of control channels does not scale proportionally. It scales at a slower rate. So with things like maybe 30 control channels, you can start to control thousands of valves. It's a very nice scalable technology. So I mentioned that these types of valves do require a lot of off-chip control. So this is what the microfluidic chip might look like, and you can see all these aluminum tubes coming out of the chip. These aluminum tubes are actually these things that are supplying gas pressure into the chip. They're being used to control those pneumatic valves. Okay, each one of these aluminum lines is controlled by an external solenoid valve, which you can purchase. It costs maybe a few $100. All right, so we talked about different ways this technology can be scaled, and then we talked about another type of valve, which is a doormat valve. The difference between a doormat valve and a standard Quake valve was that the doormat valve was normally closed. PDMS, the diaphragm valves were normally open. The doormat valves also form better seals. Excuse me. They form better seals than the standard Quake valves. So there's some advantages to these types of devices, but they're a little bit more tricky to fabricate. All right, we talked about some sidewall microvalves. An advantage of this technology was that it's only one layer device. The valves are actually move in plane rather than out of plane. And we talked about a few other technologies. So what we ended off with last time were these pneumatic oscillator circuits. And I showed you this video from Elliot Hui's paper that was published a couple years ago, where they started to create some very complex pneumatic components. They're working on building a pneumatic computer. And they built these pneumatic equivalents of ring oscillators. Ring oscillators generate an electrical pulse, an electrical clock in microfluidic, I'm sorry, not microfluidic chips, in microelectronics, your microprocessors, everything in a microprocessor runs on the basis of a clock signal. Clock signal is a square wave that goes from high to low voltage, and it just alternates between the two. So those types of square waves or timing generators are used in microprocessors. They're also used in cell phones. Like how your cell phone works at 2.4 gigahertz. Well, there's something in your cell phone that generates a very precise timing signal of 2.4 gigahertz. Okay. Now those particular clock signals are generated using a slightly different technology, but in microprocessors, these types of oscillators, ring oscillators are often used to generate oscillating frequencies. So you can generate oscillating pneumatic components too by creating the pneumatic equivalent of this electrical circuit. And what we saw is one of the nice things that you can do there is that you can start to create 3 successive valves that are operated in sequence like this, and that can be used to pump fluids from place to place. All right. Now we rushed through this a little bit at the end, but the point, what's really interesting about this technology compared to what's previously been done. I mean, you can look at it and say, oh, that's pretty cool, but how is it useful? Well, the interesting thing about this is that you can perform like pneumatic control with just a single pressure input. So I said, like with these Quake valves, you require all these different aluminum tubes, and these are all connected to external pressure controllers. So this particular one may require 20 different external pressure controllers. If you can avoid the external pressure controllers completely and have your microfluidic chip contain all that intelligence, so the microfluidic chip knows when to actuate certain valves on its own. That's what this type of technology is doing right now. So just with a single vacuum source, the chip intelligently controls its valves on its own. It's pretty neat. Pretty neat technology. So this work was done by Elliot Hui's group, but if you're interested in this area, in learning about pneumatic oscillators and these complex pneumatic logic, there's some nice review papers, including this one that was written in Lab on a Chip 2011. For a lot of the links now in our notes, I'm including, for a lot of the citations in our notes, I'm including links to the papers so that you can go to them. Again, you should be on campus or using VPN if you want to access these papers, because they do require a journal subscription. All right, so today we'll start with continuing on talking a few more things about microvalves. This is another elegant system that was done by Shu Takayama's group, also at the University of Michigan. This technology uses Braille actuators to control microvalves. So this technology is again getting at the same problem I was just talking about a few minutes ago. If you use the Quake valves, you need to have separate, you need to have a bank of these pneumatic pressure sources. Each one is about this big, costs a couple $100, and if you need to have 20 of them, you can imagine that's about $4,000 right there, and it'll take up a big space in your lab. One of the things that people often talk about in lab on a chip technologies is that we need to truly make it a lab on a chip, rather than the opposite, which is a chip in a lab. The chip in the lab technology is kind of like where a lot of research labs. If you go into my lab, for example, you'll see a small microfluidic chip, but you'll see a microscope, you'll see pneumatic controllers around it, you'll see like a liquid chromatograph next to it. So it really takes up half a room, even though the chip is only this big. To make true diagnostic technology portable, you have to make the entire system small, right? So many folks have investigated ways to use where these valves and even the pumps that we're going to talk about next can be run using miniaturized components. They don't need big syringe pumps or big pressure sources to run them. This is an elegant work because it uses something that's already manufactured and already commercially available to to control microfluidic chips. Now, if I can just let me open up a browser window here. I'm just going to type in Braille display here and show you an image of it. So this is a good one. Good old, Wikipedia, always useful. So this is a refreshable Braille display. Okay, a Braille display is for someone who is blind, right? A person who is blind can feel the indentations and the bumps in the Braille display, and they use those indentations to read. Right? Now, if you've gone to an elevator, you'll see that the Braille displays are next to the elevator buttons. Those are fixed. That's fixed Braille, right? Once you make the sign, you can't change it. Now, programmable Braille displays or refreshable Braille displays have a bunch of these little inflatable or actuatable components in it that go up on their own, right? So, if someone wanted to read a book, for example, they could read one line. They could run their finger across this thing once. And the thing is, the system gives a certain pattern of certain pins that are off versus on. And then when the person runs their finger over it again, it'll have a different pattern. So by doing this, the person can read line by line. The display itself is always, it's constantly refreshing. After the person is done reading a line, it refreshes to the next line. Right? So from a microfluidic standpoint, the student who did this I was actually at Michigan at the time this paper was published. The student who did it was actually an undergrad, and it was a paper that was published in a very famous journal that a lot of researchers who've been working for decades never get a chance to publish in that journal. So it's really impressive work. But the reason why people liked it so much is because it used a technology that was already available to control microfluidic chips. So these pins can go up and down, right? If you have a pin that can go up and down and you put a microfluidic chip right over it, you can imagine that those pins can be used to control flow within a microfluidic chip. So that's exactly what they did here. So they had a Braille display sitting underneath the microfluidic channel, and there's a thin membrane separating the Braille pin from one of the channels. Now this pink region, or the red region here, they call that the piston layer. Okay, the piston layer is filled with some type of fluid, and when the pin is actuated upwards, the fluid flows this way, and it actually ends up pushing down on the actual fluid layer, the fluidic channel. Okay, so this red layer is sort of like the control layer, except instead of being controlled by gas, it's being controlled by, it's filled with liquid, and it's being actuated by this Braille pin. When this thing goes up, this portion of the channel pushes down, and the channel is blocked. So it's basically a different way of providing this control layer. Now the cool thing that Braille displays, each Braille display may have hundreds and sometimes even thousands of pins on them. So they're leveraging a technology that already exists. In Braille displays, you can control which pins are going up and down. So they have a nice way of scaling up to being able to control many channels at once. So this is an inexpensive and programmable way to control the valves. One of the downsides, though, compared to the Quake valves, is that the pins themselves are a little bit larger. They're 900 micrometers versus 100 micrometers, roughly 10 times larger than the standard Quake valves. So this large pin could be connected to a very small channel. Like the channel, it doesn't have to be larger. This could still be 100 microns. This control channel could also be 100 microns. But the piston itself has to be larger. So the device does require a slightly larger footprint. So another way that we can think about controlling valves is by expanding or contracting a material. So this is a microvalve based on the thermal expansion of PEG, polyethylene glycol. PEG is a polymer. Does anyone remember what PEG was used for from the last module? Yeah. To prevent biofouling, that's right. It's one of those coatings that prevents protein absorption. So, BioMEMS people, engineers in general, they like to reuse material, right? If you have a material in your lab and you're using it for X, why not repurpose it for Y, right? So, materials, you'll see certain classes of materials appear over and over again when we look at BioMEMS. So, this valve is based on the thermal expansion coefficient of polyethylene glycol. Now, many materials have what's called the thermal expansion coefficient. What that means is that the material expands when you heat it up, and then it contracts when it cools down. Most materials do this in some form or another. So temperature-sensitive polymers like PEG and wax can be used in this type of a doormat valve design. So we've looked at doormat valves before. You can see this is basically a doormat valve design. As a reminder of what that is, it consists of a membrane. The membrane is shown in black. It consists of a larger cavity at the bottom and a small post at the top. The post is referred to as a boss or a valve seat. From the top view, the diaphragm valve looks something like this. Okay, there's a flow layer going across here, and this black circle here is this membrane layer. Okay. Now, when the valve is open, like this, when the membrane is deflected, you can have flow going from left to right. And when the valve closed, now this prevents flow from going from left to right. So one way of controlling the on and off state of the valve, we talked about using gas pressure to do it, so that's obvious. But you can also use a polymer. In this case, a polymer could be introduced in the molten state. When the polymer cools, the polymer will contract and the valve is open. And if you want to close the valve, you heat up the polymer, and so it expands like this, and it closes the valve. Okay, so this is a temperature-based actuation. What's called a well, not exactly thermopneumatic. This is a thermal expansion valve. So one of the reasons why people would go to a technology like this is so that it can be electronically controlled. You can make small heaters on the chip, basically a resistor, an electrical resistor. You run current through it. It heats up the area, increases the temperature. And if you have something like this that responds to a change in temperature, then now you have an electronically controlled valve. The downside of this type of approach is that the temperature-based actuation is relatively slow compared to other approaches, because it takes time to heat up and cool down something, even at the microscale. Remember we talked about that in microscale devices, heating and cooling can happen relatively rapidly compared to the large scale. That being said, it's slower than other types of actuation techniques. Electrostatic techniques, for example, can open and close valves within tens of microseconds, much faster than this. You're talking about tens to hundreds of milliseconds, okay, which is relatively slower. So other types of technologies folks have looked at is the pH-sensitive valve. So these are valves that respond to a phase transition, or I'm sorry, the valve material itself undergoes a phase transition. And this is the title of the slide says pH sensitive, but it could also undergo a phase transition depending on pH, temperature, or even light. So how it works is that the polymer posts are photopolymerized inside the channel. We've already talked about photopolymerization, right? You have your channel, you flow the liquid polymer through there, and then you basically shine a beam of light into certain areas of the channel. That beam of light polymerizes the liquid and turns it into a solid. So that's how these types of valves are created. Now these posts are made up of a special polymer which can expand or contract depending on the pH. In this particular example, they were showing that the size of the two valves depending on the pH. Now, the valve on the right, if we take a look at that, when it's at 4.7, the valve is in a smaller state. And when you increase the pH, so when you go to a more alkaline state, the polymer responds to that. It swells. And when it swells, it blocks this portion of the channel. The valve on the left side is designed so that it does exactly the opposite. The valve on the left will actually contract at alkaline pHs, at higher pHs. So you can have a situation where you can have fluid flow in one direction if it's a certain pH, and you can have fluid flow in the opposite direction if you're at a different pH. So these types of microvalves have a relatively slow actuation, 1s to 10s of seconds, but they're based on a volume change. There are many materials that respond to the pH content.
So this microvalve is for keep the solution neutral, pH.
This particular, well, the way that they design these microvalves is to route fluid from one direction to another depending on its pH. The focus of this paper really was to just show that you could have these valves that open and close based on pH. Just like this valve open and close based on temperature, this one can be done based on pH. Now there are other types of valves that respond, like I said, to temperature. There are also certain valves that respond to light. Okay, but just as a general principle, keep in mind that if you're talking about a polymer that expands and contracts, that's a relatively slow process compared to other, compared to, say, electrostatic valve technology. All right, let's talk about a few other types of valves here. So we talked about this concept of check microvalves last time in lecture. Check microvalves are valves that are designed to only allow liquid flow in one direction. So remember we were giving this example last time of this type of, there's a ball check valve. So when you have fluid going from the top of this device to the bottom of this device, it's going to push the ball away, so it allows fluid to come through. If you try to run fluid in the opposite direction, that's going to force the ball into this flange, and this will block the fluid flow. These types of check valves, the type you have in your toilets, would consist of like a rubber seal that opens when you run liquid in one direction, but when you try to run liquid in the opposite direction, that flap closes, and that's called a swing check valve. So this type of technology has in fact been miniaturized using surface micromachining, and it can be used to regulate sample flow. Right, so basically it uses a flexible flap made from a thin film material, or perhaps even the thin film material might also be flexible, something like PDMS. So in this example, the fluid, the sample comes in like this. All right, so this will be at a high pressure, and then the reagent would have to be at a higher pressure, so P2 would have to be greater than P1 in order for this check valve to be open. Okay, and this is sort of the outlet where the two mixed components come out. Okay. Now this is a relatively crude device that's just all it's doing is mixing two fluids, right? But it does show the operation of what a check valve can do. The way that this check valve would be fabricated is by, well, I don't have a diagram of the fabrication here, but this was done using surface micromachining, where they created they did an etch through the back of the wafer here, and then they had a sacrificial layer. They deposited this flexible layer on top of the sacrificial layer, and they removed the sacrificial layer at that point. So it was a surface micromachining approach, and that's how you get basically this small film that's also free to move. It can move up and down. So this is an example of a check microvalve. We'll talk about the importance of check microvalves in later on today when we talk about diaphragm pumps. There's other types of valves. There's a couple ones that we can talk about that are designed for one-time use. One is called the capillary burst microvalve, and the other one are based on sacrificial membranes. So let me give you a little bit of a background for this. Why we would want something like this. A lot of microfluidic devices and BioMEMS and lab-on-a-chip devices are designed for one-time use. And you can think about why just by think about when you go to your doctor's office, right? When you go to your doctor's office, the tubes, the test tubes that they use to collect your blood, the little the assays that they do, everything is pretty much one-time use. They dispose of it, right? We talked about this in the fabrication module when we were saying that, well, microfluidic devices or lab-on-a-chip devices need to be made relatively cheaply because a lot of times they're going to be disposable. Well, your valve technologies can also be one-time use. Maybe you're just going to be using it a single time. So here are a couple examples of that. The capillary burst microvalve. So this is talks about the passive control of fluid flow. The way that this is based on is an abrupt change in the width of the channel. Do we have a picture of this? Okay, we'll get to the details of this a little bit later. So I'll just describe it in general terms right now. If you have an abrupt change in the channel geometry or the surface chemistry, you can have a sort of a system where the fluid itself will block itself once it gets to a certain region of the channel. This is an example of where you have a small channel going into a larger channel, and right at when this fluid forms a meniscus between the small channel and the large channel, that acts as a valve. Why does it act as a valve? Well, you have a meniscus forming here, right? Now, what happens when we form a meniscus? Do you guys remember from the last module? Hydraulic resistance. Close. Not quite a hydraulic resistance. It's a pressure that forms. A Laplace pressure. Remember we said there's a Laplace pressure is 2 multiplied by the interfacial tension divided by the curvature of the interface. So whenever you have a curved surface like this, so this is liquid and then this is air. Whenever you have a curved surface like this, you end up getting a Laplace pressure that develops between these two regions. And that Laplace pressure, it pushes back. Now the way that you can think about this intuitively, think about surface tension here. Right. Surface tension are these water molecules that are basically trying to attach to each other. They don't want to break. They want to stick to each other. And so that forms a tensile skin across this interface here. That tensile skin, if you imagine a balloon on one side of this thing. If you're trying to push that balloon out of the channel, you're going to end up this balloon is going to actually push back with some amount of pressure. So this liquid, just on its own, it actually pushes back with some amount of pressure. And so that is what they're calling a valve. The reason they call it a valve is because normally it'll basically block the fluid flow, but if you put enough pressure on it, the valve will actually break, and then you'll get the fluid flow through there. Right? So this type of valve is called a burst microvalve, is because it's a valve that can break. But it's useful for if you want to meter a certain amount of fluid into the channel. For example, if you're loading a reagent from this side, the fluid will come here and it'll stop here on its own. So this region of the channel is filled by the fluid. So you're metering a very specific volume of a reagent into the channel. So if you want to add a very specific amount, like 10 nanoliters of this reagent into your assay, you want to measure that out, then these types of capillary valves could be useful. All right, like I said, once the liquid pushes past, once the capillary valve breaks, then this region can fill into the rest of the channel. Next, these are membrane microvalves. Who was I talking to? Nick, I think we were talking about this the other day. Nick's was interested in doing a project related to drug delivery. So we were talking about ways that you can deliver doses of drug into the body. And this was one of the papers that was, the concept of it was very interesting. I don't know if it was actually ever put into practice. This type of valve could be used for, potentially be used for drug delivery. The idea behind this is that you'd have a whole bunch of pits. So let's say you had a silicon substrate here, or whatever type of substrate, and then you had pits inside of it that was filled with drug. Now, when you wanted to deliver just one dose, like today's dose of the drug, you could basically break the membrane on top of it. They call it a sacrificial membrane. All right, and the idea behind this was that, let's say you had like a small chip that had 10,000 different wells in it. Then if you're opening one of those wells per day, then you could have 10,000 days of drug in there, right? So that was the idea behind this. Now, in order to make an idea like this work, each of those valves or containers must have a seal on it, and that seal, you have to be able to break it somehow. So this sacrificial membrane was made of gold, and the gold could be electrochemically dissolved if a 1-volt pulse was applied to it. All right, so this was the cathode. They had one common cathode, and each one of these different valves, or each one of these different membranes would be the anode. Right, so if you wanted to break this one, for example, you apply voltage between the anode and the cathode here, and there's an electrochemical reaction that would occur that would dissolve the gold, leaving this region open, and then the drug could basically diffuse into the body. So it doesn't necessarily have to be made of gold. There's other types of sacrificial membranes. You could have two made of nitride or SU8. You don't necessarily need to use an electrochemical potential. You could use something that is made from something that when you increase the temperature, it dissolves. Something where you could run a current through there, it dissolves. And there's even a lot of polymers that just dissolve on their own in the body. Okay, and the ones that dissolve on their own are actually the ones that are used commercially. There are, I'm sure that at some point you've probably gone to the store and bought extended release drug capsules, right? The type of drug capsules where the drug is released slowly inside your body over the course of, a week, a day, or even some cases months. a month or two. In those cases, those pills or those things are actually made up of a polymer that's designed to dissolve in your body. It dissolves on its own. Your body's natural, the fluids in the interstitial space or wherever that the pill is ingested, that the polymer is designed to dissolve within your body. As it dissolves, it contains the drugs. It releases the drugs into the body as it dissolves. It's a very elegant way of doing long-term drug delivery. That technology was a lot of it was commercialized by Bob Langer's group, who's a professor at MIT, and he has I think something like more than 50 startup companies that he's began for various technologies. He's a very prolific inventor. So if you're interested in polymer drug delivery, you can look up his lab, Robert Langer. So since we're talking about valves, it's also worth it to talk about this technology, which was done by Rustem Ismailev's group, who is he is at Caltech right now. This is a valveless way of doing biochemical assays on chip. So you can look at it as the antithesis of valves, or you can look at it as this is actually a type of valve. So it depends on your interpretation of what's being done here. In a lot of times in microfluidic experiments, we want to do what's called a screen, where we combine a set of reagents with a target. So let's say we want to we have 30 different drug compounds, and we want to test each one of those 30 different drug compounds with a certain cell type to see how the cell responds to it. So Ismailev's group designed this cool thing called SlipChip, which allows you to do this type of test in a very simple way, which requires no external pumps, no external valves, because they use a sort of this cool valve technology that's built in on the chip. That's very, very simple and elegant. So let's look at how this works. There's a two-layer chip. Right, one layer contains the one layer contains these wells, okay, square wells, and the other layer contains a fluidic channel that looks something like this. Now, what's the best way to explain this? All right. Let's see. So let's say this. Let's say they have a two-layer chip like this. The reason they call this SlipChip, by the way, is because they have two chip layers that can slide upon each other. So let's say you have two layers of PDMS that look like this. Okay, this is one layer, and this is another layer. that was L2, L1. Now initially what we did is we filled up one of these little well regions, and this is, by the way, it's a sort of a square-ish region here like this. I'm going to just delete that just for clarity's sake. Now I've drawn these two layers with sort of a space between them, but there's actually no space between them. Okay, they're pushed up together, so they form a seal. And there's actually a fluorocarbon liquid in between these two layers. Okay, that seals these fluids into the chip. So what they do is that they have a channel layer. They run, let's see. So let's say they run a certain a target into this fluid layer, or into this channel layer. Right, so they're flowing this in here, and as a result, this area, this portion underneath the chip gets filled with a certain target like this. Now this channel can also get filled with this reagent. But what they do is, if they want to combine this one with this one here, all they do is they fill up this channel and then they slide the whole chip over like this. They slide this entire layer over manually from one place to another. And what happens is that this basically moves over to here, and then the two of these things combine. So that concept is, it's a very simple concept, but they've really taken this idea and really expanded this to do some very interesting things. Right? So those two layers that you see here, you can kind of see that this green layer here is being flowed from left to right across the chip, and it fills in some of those wells, okay, across the middle here. Then in previous steps, they had filled in all these these other wells here, showing the blue, yellow, and the red. So those were filled in a previous step. In fact, those were filled in when the channels were vertical. So if you want to fill in all the blue things here, you could fill in by putting in a vertical channel like this. You fill in all the yellow and red ones in a similar manner. So the steps would be something like this. After you fill in your reagents here, you can add your sample here at the bottom. Right, and this these wells fill up with the green liquid, and then you slip this region over, and now you can see that those two regions match up and the two regions basically come together, and then the two chambers end up mixing. So if you wanted to do this in a traditional microfluidic chip, that would actually, you'd have to have several inputs and valve controls and things like that in order to get this series of fluids to mix the way you want it to. But this really doesn't require any valves at all. It just requires the lining up of the different chambers in order to get the chambers to line up with one another, so the reagents can mix with one another. So sometimes the best technologies are the simplest ones. And so they're actually commercializing SlipChip technology for many applications. They're a company right now. They've successfully used it for doing screening and protein crystallization and digital PCR. So again, I brought this up because this is sort of a valve-less approach to doing multi-step assays. Okay, a couple more topics here. Then we'll take a short break. Other types of valve technology. So we talked about the pH-sensitive valves, optomechanical valves. Instead of responding to changes in pH, they respond to light, and these contain nanoparticles, with well-defined optical absorption profiles that are mixed into a thermally responsive hydrogel to make it light sensitive. Basically, these nanoparticles absorb light, they heat up when they absorb light, they heat up the polymer, and the polymer either expands or contracts depending on depending on the light source. So they showed different examples of this here, where either the polymer can swell or deswell based on the amount of light going into the polymer. So we were talking about valves that can be controlled using pH, temperature, and then light. This is an example of a valve that can be controlled using light. One of the applications of valve technologies is to make something called microfluidic resistors, or microfluidic potentiometers. So in last module, when we were talking about, laminar flow, we talked about how Kwang-O's paper, how they had different lengths of channels, and each one of those channels had different resistances. Longer length channels had larger resistances, shorter length channels had shorter resistances. This example on the right here shows how you can change the resistance of a channel by activating or deactivating valves. So if we look at something like this, relatively simple concept here, the resistance of a microfluidic channel depends on its length. And this is a way that we can basically control the length of the channel. By opening and closing certain valves, we can direct the fluid into the shortest path to the output, or we can direct it into segments that make the effective length of the channel longer. All right, so if we close this switch, for example, the current can flow directly this way. If we close this valve, then the fluid flow can go directly from top to bottom here. And if we close it off, the fluid will have to be forced to go through this longer path like this. Okay, so you could have a series of valves that controls segments of different lengths, and by controlling which segments are turned on and which segments are turned off, you can get, in this case with 4 valves, you can get 2 to the power of 4 different combinations of resistances. Because if you have 4 channels in each one of those, if you have 4 sub-channels and each one of those channels can be turned on or off, then you can have a total of 16 different combinations of which channels it's going through versus which channels it's not. So you can get 16 possible resistances there. So this is a digital control of flow resistance. So an analog control of flow resistance uses these things called inflatable elements. This varies the flow resistance by adding 1 or more barriers of variable flow resistance. So again, a relatively simple idea. You have liquid going through the fluid layer, and by pushing this membrane up, so the membrane gets pushed up by pneumatic pressure, then the fluid has less room to move through. So this is going to increase the hydraulic resistance. Remember, the hydraulic resistance is related to the channel dimension to the 4th power. So you can control the resistance quite a bit in this manner. You can greatly increase the fluidic resistance by basically deflecting this membrane. So these are examples of different microfluidic resistors, where you have a series of valves here in each one of these guys, and you can control whether those valves are on or off. And the more of the more of these elements that you push up, the more fluidic resistance you'll have. So in this example, channel A has a lot of fluidic resistance here, so there's going to be very little flow of A. You can see at the bottom here that these laminar streams, when they combine, that there's very little flow of A here compared to B and C. Right? Just by controlling the different fluidic resistances, you can get different mixing ratios of the three fluids. So these are both relatively straightforward concepts. All right. Extending this a little bit further, you can create these things called binary multiplexers. Okay, again, these are all based on valves. If we looked at the Quake microvalve, the best way to understand these things is by starting off with a thing that we looked at earlier. The key thing about a Quake microvalve was that it's a multiplexer that has several inputs and it only has a single output. Meaning that it may have 8 different inputs, but only one of those inputs are allowed to flow to the output. It's an N-to-1 multiplexer. So in this example, channel 3 is allowed to go to the output. The way this thing is designed, there's no possible way for more than one fluid to go to the output. So this type of device is good when you want to select a single input and take it to the output. It's not that suitable if you want to mix one or more elements together. So by modifying the Quake valve scheme into something like this, into these different designs, well, it's just a single different design. Into this different design, you can get what's called a binary multiplexer. So this is a different multiplexer design that allows multiple inlets to flow to the outlet. And everything about this is actually, it's very similar, except you'll notice just some changes in how the valve structure is. Okay, let's look at some of these differences here. In the Quake valve structure, you have the bit 3, okay, the most significant bit, that has a valve structure that looks like this. It's a wide here and narrow here. So that means that this pneumatic input is connected to channels 0 through 3. This pneumatic input is connected to channels 4 through 7. If we look over at this example, we see the same sort of thing. 8 here and 8 here. Now if we looked at the next bit, all right, we see that there's a connection here at 0 to 1. Then the complementary bit, or the complementary portion of that bit, is going over 2 and 3. Then this channel is going over 4 and 5, and then this channel is going over 6 and 7. So the pattern here, you'll notice, is slightly different. Okay, this one is connected, and then this is connected, so it's alternating. It starts off looking the same, but then this pneumatic, the next 4 valves is connected in the same line, this V4 line, okay, rather than you see an alternating pattern here that goes up and down like this. You see something that looks like up, down, down, up. The Quake valve scheme was up, down, up, down. Okay. I'm trying to get at the main point here, which is that by controlling these regions, okay, the regions where the pneumatic control channel interacts with the fluid channel, that only happens when this region is wide. Okay, there's no interactions happening here or here. It's only happening in the regions where this is wide. Okay, by controlling the regions of interaction like this into a slightly different pattern, you can get from an N-to-1 multiplexer to a multiplexer where you're combining one or more streams of fluid together, as you can see here. So this type of binary multiplexer will allow you to put in a code, like you put in here, a 3-bit code controls which line goes to the output. In this case, a 3-bit code or 4-bit code controls which of these inputs are mixed to one another. Okay. So in this binary multiplexer, by controlling the 4 different bits of input, you can essentially control um, that you can control the mixing of 16 different inlets. All right. Before we go on to micropumps, why don't we take a short break, 3-4 minutes, just to breathe a little bit and get a drink of water, and we'll continue from there. Let's pause this. All right. So talking about micropumps now. So this is obviously an important part of lab-on-a-chip devices. Micropumps are used to move fluids from one place to another. They're used for delivering biological samples in microtests. This is what's called the in vitro diagnostics. In vitro means outside the body. In vivo means inside the body. So pumps are also used for in vivo drug delivery. So we were just talking about, before break, we were talking about how if you may implant a device in your body that can deliver drugs into your body. Micropumps are actually also being used for ex vivo drug delivery as well. Medtronic currently has a product called a insulin pump, or a continuous glucose monitoring system. It monitors your glucose, and at the same time, when you need insulin, it will deliver insulin into your body. This is for people who are diabetic. So they actually have the pump sitting outside of your body, but there's a tube that goes inside. Right? So, that's an example of ex vivo drug delivery. You still need a pump to meter and control the fluid going in. Micropumps are also used for micro heat exchangers. These are more for semiconductor applications, for cooling down electronic chips before they get too hot. But these are different applications of micropumps. The categories, 2 different categories of micropumps. There are the passive pumps, which require no energy input. These types of pumps offer simplicity, but only a rudimentary level of fluid control. The active pumps, by comparison, they actually require some sort of actuator or field. You need to put energy into the system somehow. And these are a little bit more complex, but they also allow for more deterministic control of the fluid flow. So think about an example of an active pump would be a piezoelectric pump. You actually have to drive that piezoelectric pump with an electrical source, right? An example of a passive pump would be a capillary pump, which just works on the basis of surface tension. So there's nothing that you need to put, no external energy that you need to put into the pump. So we'll look at a few different examples of that. And how do you judge a micropump? Well, if you are here and you need to select a micropump for your class project, let's say you decide to do a device that requires some type of pumping mechanism, you would choose a pump based on their ability to provide a certain amount of pressure. That's called the back pressure. Some pumps can provide a lot of pressure. Some pumps cannot. You can judge them by their ability to provide a certain flow rate, by their size, fluid compatibility, and power consumption. A lot of times, the pumps, you're limited by, if you want to use the simplest thing possible. Right? So folks have come up with interesting ways to do pumping that are actually quite simple. The most recent ones, which I'm not sure we'll get to talk about in this module, but the most interesting types of pumps now are the ones that just rely on paper. You put a drop of water on paper, and the water just spreads out by capillary action. Right. Those types of paper microfluidic devices are used in a lot of lab-on-a-chip type devices nowadays. But for the purposes of this module, I want to show you the different active and MEMS-based technologies that are used for micropumping. Just so this is for an educational purpose, so you can kind of see the broad scope of technologies that are out there for pumping. All right, so the first one we'll talk about here is a passive capillary micropump. Passive meaning it doesn't require any external energy input. It's a relatively simple device in that sense. So this is how the device works. You have an aliquot of liquid that's placed into the device. Surface tension will wick the fluid into one of three parallel channels. Let's see, how can we explain this? Okay. Let's go back to a concept that we are familiar with. Oops. We were talking about the capillary burst microvalves. So let's say you have this portion of the channel that's filled with liquid, and this is gas. And the liquid forms a meniscus here. Okay. Here, you're going to end up forming a delta P, Laplace pressure. So if you have a droplet, you have a delta P that forms, and this delta P is equal to 2 times the interfacial tension divided by R, the radius of the droplet. We've seen this formula before. Right? But whenever you have a curved surface like this, you also develop a Laplace pressure. Okay, and that Laplace pressure is inversely proportional to the radius, and it's proportional to the interfacial tension. So what this Laplace pressure does is that it actually prevents the fluid from from going out into this larger space, into the wider space. Now, notice that the amount of pressure that this valve provides is inversely proportional to R. So it really depends on the size of the channel. The smaller the channel you have, the more capillary pressure is going to be built up over that region. So this device takes advantage of this basic phenomenon. Let's go up here. Okay. So an aliquot of liquid is placed into the device. The surface tension capillarity wicks the fluid into 3 parallel channels. Once the rear meniscus reaches the capillary retention valve, it is pinned there and the liquid flow stops. The CRV has the smallest dimensions and therefore the largest capillary pressure. That's the key concept here. The CRV is called the capillary retention valve. So let's go through this step by step. All right, this thing, let's see. First you start by pipetting the liquid into this device. There's a section of this device that has a cover over it. Now notice the curvature of the liquid here. The liquid is curving towards the channel. This means that the channel is hydrophilic. Okay. If the channel is hydrophilic, the capillarity is going to wick the liquid into the channel. Okay, because the liquid likes the surface of the channel. The surface is hydrophilic, the liquid is aqueous, so the liquid likes the surface of the channel. The channel pulls the liquid in like this. Now, where it stops is when the end of the fluid reaches a capillary retention valve. Notice that in this region, okay, you have this capillary pressure forming. Yeah, I hope you can sort of see this here. So we have a situation here where we have a meniscus here on one end. This is generating one capillary pressure, right? And then we have these three menisci on the other end, which are also generating a capillary pressure. The menisci on this end is pulling the liquid forward, like that. And the meniscus here is pulling the liquid back. So it's a tug of war between these two capillary pressures. Now, why does this one win? Well, there's three capillaries here. They're all pulling with a certain amount of capillary pressure. And furthermore, these three capillaries have a small radius. This one has a much larger radius. If we look at this formula for capillary pressure, this is slightly different from the capillary pressure for a droplet because now we're dealing with a rectangular channel rather than something that is axisymmetric. The formula for capillary pressure in a rectangular channel looks something like this. There's a cosine of alpha plus cosine of alpha divided by d. D is the depth of the channel, and these alphas are the contact angle of the liquid on the bottom and the top of the channel. Then you have this other term representing the contact angles on the left and the right of the channel. This should be R, by the way. L and R, and not T here. And there's the width of the channel here. But you can see that the capillary pressure is inversely proportional to the dimensions of the channel. So the channels that have a smaller dimension are obviously going to generate a larger capillary pressure. So these guys are generating a larger capillary pressure than this side. So the fluid gets pulled up further. Now when it stops is when it reaches this thing called the capillary retention valve. A capillary retention valve is nothing but just a thinner region of the channel, a very narrow channel. When it gets to this portion here, this channel is so narrow that it generates a lot of capillary pressure. So remember that the capillary pressure is inversely proportional to the channel dimensions. Okay, it's a nonlinear function. So when you have a very small channel like this can generate a lot of capillary pressure, enough to overcome these guys, even though that there are three of them pulling. There are three of them pulling, but the radius is much larger, so the total capillary pressure on that end becomes equal or less than what is provided by the capillary retention valve. So as a result, the fluid flow basically stops at that point. The pipette comes in here. This is the second step of the assay. You're adding your second reagent, and the second reagent comes in and fills in these regions, and the two fluids mix together. And again, it stops when the total fluid reaches the end of the capillary retention valve here. Right, so everyone kind of see how the capillary retention valve works? Right, so this demonstrates a lot of different concepts. I mean, one main concept here, which is the simplest one of all, is that fluids, if you want to pump liquids into a channel, if the channel is hydrophilic, you don't really need to do anything at all. The channel itself will wick the fluid into it. That's the first concept, and that concept alone has been used in a lot of different types of micropumps, a lot of different types of microfluidic devices. In fact, this type of thing is used in your doctor's office too. Have you ever noticed when you get blood draws, the first thing, it used to be, I don't know if you guys remember this or not, they used to take, or when they're doing big blood draws, they'll take a syringe and literally like pull your blood out of you like a vampire, right? That's when they need to draw a lot of blood. But nowadays what they do, if they're doing smaller amounts of blood, they just prick you with a pin, and then they take a very tiny capillary. I don't know if have you guys seen this before? Like a very narrow glass capillary, and they'll just take that capillary and put it next to the blood, and your blood will automatically fill into the capillary on its own through capillary action. And when the blood fills up the capillary, that's it. It stops pumping. Does So Shirley's getting a little queasy here. This device works on that sort of principle. Right? Capillary action can literally pull liquid into the channel. So you're taking advantage of miniaturization here. This type of device takes that idea. You could say it's a step further, or you can just say it's just a very simple and elegant idea. This is a pump that's just based on surface tension. We talked about capillarity. Now we can talk about surface tension being used in other ways. So the Laplace pressure I mentioned is delta P equals 2 sigma by R. 2 sigma divided by R. Sigma is the interfacial tension. R is the radius of the bubble. Now, when you put liquids into a microfluidic chip, and you guys have made some of the microfluidic chips before, so you know what they look like. The channel layer will look something like this, and you have these two drilled inlets. You drill an opening here, and you drill an opening here to form the inlets and the outlets in the microfluidic device. Now, suppose you were to put a large drop of liquid in here, and you were to fill the channel, and then you have a smaller drop of liquid here. What would end up happening is you'd end up getting flow going this way to this way. All right. The reason why, and it's actually a pretty simple reason here. Imagine two bubbles here, okay, and the two bubbles have different radii. So you look at this formula here. The Laplace pressure, delta P, is equal to 2 sigma divided by R. So if you have two bubbles or two drops on either side of the channel, the inlet versus the outlet, they're going to determine different amounts of pressure. So which one is going to develop more pressure? This side or this side? Left side or the right side? The right side, because the radius is smaller, so the Laplace pressure is larger. This is a very easy way to do pumping. So if you start out with this side just a little bit smaller than this side, you're going to have flow going from right to left. And as the fluid gets depleted on this side, this is going to become even smaller. So the pressure would even continue to increase. So it'll continue to pump. All right, and this one, the radius is going to get larger and larger. So you're going to have less pressure coming from there. So this type of pumping is just based on the fact that the two drops on either side have different Laplace pressures associated with them. Now, if you were to analyze the system in more detail, you'd also have to include the hydrostatic pressure of the liquid in this column versus this column. Okay, there's a certain hydrostatic pressure due to the weight of the water, and that hydrostatic pressure is called rho GH. Or the formula for it is rho GH, the density times the gravitational constant times the height. Yeah, and if you want to confirm this, you can look back at our notes a couple modules ago where we talked about hydrostatic pressure. So the full analysis will actually include this Laplace pressure effect and the hydrostatic pressure effect. But again, this type of thing becomes, it's a pretty simple way to create a pumping effect and flow. All right, in the last 10 minutes, let's start talking about active micropumps, and we will continue this discussion after. We'll continue this discussion on Wednesday and try to finish it up then. So active micropumps are when we're actually putting energy into the system. We're controlling the flow deterministically, usually by some type of electronic control. So within the scope of active micropumps, there are two basic categories, and those categories were described in this paper, 2004 paper, a review of micropumps. If you type in micropump review on Google Scholar, you'll get about 10 different articles, 10 different review papers that talk about developments in the micropump field over the last 10 years. If it happens to be an area where you're interested in doing your project, then you can definitely, I would suggest looking at that. So let's talk about some of the different types of pump technologies. One category of pumps is called the displacement pumps. Displacement pumps exert pressure on the working fluid through one or more moving boundaries. And probably the most well-known example of this is the peristaltic pump, the ones that we saw an example of several slides earlier, where you have these membranes that are pushing down on the fluid, and as they push down on the fluid, they generate flow. Okay, that's called the displacement pump because the membrane is displacing, it's moving, and it's pushing fluid out. So the membrane is exerting pressure on the working fluid. The other type of pump is a dynamic pump. It continuously adds energy to the fluid by increasing its momentum. So examples of this would include centrifugal pumps. Centrifugal pumps are kind of a cool way of pumping liquids where you put, let's say you have a CD, spinning disc, okay? And you put fluid in the middle of the CD. What happens? What do you think will happen to it? It goes to the outside. Yeah, absolutely. It spreads out to the outside, right? Because of centrifugal force. So that's an example of a dynamic pump. Spinning the disc is adding centrifugal force into whatever liquid is there, and that's pushing the liquid out. Another example is this thing about electroosmotic pumps. This is a type of pumping mechanism where you just put a voltage across two ends of the channel and the fluid starts to move through the channel just by applying the voltage. So in this case, you're adding electrical energy into the system, and that electrical energy is being converted into a pumping mechanism. There's other examples: electrohydrodynamic pumps, magnetohydrodynamic pumps, acoustic streaming pumps, and so on. A few different examples of that. So these are the different types of dynamic pumps. Now I mentioned when you're looking at different types of pump technologies, what are the things you're looking at? You're looking at the, what kind of flow rate can you generate? What kind of pressures can you generate? What is the size of the pump, the power consumption, and the compatibility of fluids? Also, I should add in here the cost and the simplicity to make. What type of materials do you need to make the pump? That's also a consideration. One of the things you may notice just from a practical standpoint, out of all these different valve technologies, I would say two of them have actually gotten some commercial traction. And that is the diaphragm pumps. This is because like the Quake technology, the Stephen Quake's membrane valve technology, that's very scalable. It works relatively well. And there's a company called Fluidigm that's been commercializing that type of pumping technology. Another type of pumping technology that is very popular in analytical chemistry is electroosmotic flow. This has been used in microchips that do capillary electrophoresis, and they do chemical separations. That's going to be the module right after this one. Okay. So besides those technologies, centrifugal pumping is starting to get more commercial traction. I believe there's a commercial company that's using centrifugal pumping. And some of these other technologies are, there's been a lot in academics, but less actual industry traction. So when it comes down to it, industry tends to like the pumping mechanisms, which are very robust, easy to fabricate, relatively low cost, and provide a sufficient flow rate, a sufficient pressure, a sufficient size for whatever the application needs to be. So let's start talking about diaphragm pumps. This type of mechanism, this is an example of what a diaphragm pump might look like from the side. This is a schematic of a micropump that was made by stacking several layers of silicon together. You can see these three different layers here. These are actually three different silicon wafers which were stacked together. Let's not focus on the fabrication part of it. Let's focus on how the device works. Diaphragm pumps have a pump chamber. They have an actuator, a diaphragm, and 2 check valves. So in this case, you can see that there's a chamber here, and that chamber has a certain volume associated with it. There's an actuator, a driver, that controls the diaphragm. So in this case, the diaphragm is right here. So when the diaphragm is actuated, the diaphragm can either move up or it can move down. The expansion stroke or the suction stroke is where the chamber volume increases. And then the contraction or discharge stroke is where the chamber volume decreases. Now, the valves play a very important role here. So let's say you had a diaphragm like this, and this diaphragm was just connected to 2. Let's say the diaphragms were just connected to 2 inputs like this. Terrible drawing, but you get the idea. So you have a diaphragm that goes, it contracts up and it contracts down. So what's going to happen on the upstroke when it pulls, when it expands? Which way, what direction is the fluid going to go? Go up, that's right. So on the contraction, fluid will go up like this. Or on the expansion, sorry. On the contraction, the fluid will go, and fluid will go down. Right, when the diaphragm comes down. So that's not really useful, right? That's what we call like reciprocating motion. You know, you're pushing one way, you're pushing the other way, but you're not getting any net motion. So the check valves play a very important role. Let's go back to this. In this diagram, you can kind of see that the check valves only allow flow in one direction. During the expansion or the suction stroke, the inlet valve, so the inlet valve curls up. It allows flow to go into the chamber. Right? But notice that the outlet valve is closed. So you're only getting flow into the chamber. Now during the contraction stroke, the inlet valve closes and the outlet valve opens, and that basically pushes some fluid into the outlet. Okay. So these check valves, these devices that only allow flow in one direction, you need 2 of them in the diaphragm micropump, and it's very critical for those that you have a check valve in order for this to work. Otherwise, if you don't have the check valves, you're just going to be pushing liquid or fluid in and out of the chamber. So this is what's called, the technical term for this is rectification. All right. The diaphragm pump, the diaphragm on its own is providing multi-directional movement. It's bidirectional. But by adding the 2 check valves to it, you are rectifying that bidirectional motion into unidirectional flow. So that's called flow rectification. The check valves rectify the periodic motion of the diaphragm into a directional flow. The ideal flow rate provided by the diaphragm pump is a very simple formula. The flow rate is equal to the delta V times the frequency. Delta V is the change in the volume, exactly, the change in the volume of the chamber between the expansion and the contraction stroke. There's a delta V. And the frequency is just how fast, how many cycles per second the diaphragm is moving. So in the MEMS area, one of the advantages of miniaturization is that you can get diaphragms that can actually move very rapidly. Some of the microvalves that were being worked on when I was in grad school at Michigan was the electrostatic microvalves. They used MEMS components like this, not just at Michigan, but many places around the world were working on electrostatic microvalves. It was made up of, a diaphragm, and that diaphragm was actually an electrode. So when you put a positive charge on this electrode and a negative charge on the valve seat below it, the membrane would deflect. Kind of like the micromirrors that we talked about at the beginning. You put a voltage across 2 plates and they get attracted to one another. So Those types of micropumps actually had a very small delta V. Because the diaphragms were relatively stiff, they didn't move very much. However, they made up for that by having a very large frequency. Those electrostatic pumps only, they could deflect in like 10 to 100 microseconds. So even though the displacements were relatively small, you could still get a flow rate because you're moving them very rapidly. There are other types of technologies, thermopneumatic micropumps, where you're using a temperature to move the diaphragm up and down. Those are much slower, but they get a larger delta V than the electrostatic ones. So they still can generate flow. Okay, so that's the basic concept of a diaphragm micropump. So next, on Wednesday, we'll get into more of the specifics on the different types of diaphragm micropumps in terms of the actuator and in terms of what types of valves can be used and the scaling technologies. Then we'll start talking about other types of pumping technologies. So just to give you a quick overview of some of the things we'll cover: rotary micropumps, ferrofluidic micropumps, phase change pumps, and then we'll start talking about electrical pumps, where you can actually use an electric field or a voltage to pump liquids from one place to another. I think electrical engineers who might find that interesting. And this will lead into the next module where we talk about capillary electrophoresis, where a critical part of capillary electrophoresis is this type of electroosmotic pumping. All right, so we'll stop there for today. And Wednesday will be, make sure you get your assignments in by Wednesday. So the 2-day extension is not a problem, but Wednesday will be we'll definitely would want to get the things in by Wednesday. And then after Wednesday, would like you to just focus on your class projects. And if you have any issues or questions about the class projects, come talk to me. Between now and Wednesday, if anyone's having trouble with the COMSOL simulation, you want to talk about it, let me know. Okay? Thanks.